Hello dear students, welcome back to the chemistry class. Today's topic of discussion will be atomic spectra. We have discussed Bohr's theory, postulates of Bohr's theory. Based on this postulates of Bohr's theory, we have defined different types of calculations like radius, velocity of electron, energy of electron, number of waves made by electron during one complete revolution, what is the time required for this electron to complete an orbit, what is the shell frequency. During this discussion, we have found that as long as electron is revolving in a particular orbit, it has got a fixed energy, that is, energy is quantized. So this was the first theory which used the concept of quantized energy levels. So when the electron is moving in a circular orbit, it has got a fixed orbit, and that orbit is known as stationary orbit. So when an electron is in a stationary orbit, it does not lose energy. But if this electron is supplied energy from outside, energy will be absorbed by electron, and electron may be excited from some lower level to higher level. So during this excitation process, that is promotion of electron from a lower level to a higher level, that is known as excitation. Energy is absorbed. So depending on the quantity of energy, electron may be excited to different levels. So when we measure the frequency of radiation absorbed, those frequency, if you make a mapping of those frequencies, so those frequencies which are being absorbed will be missing in the map. That is what we call as absorption spectrum. Now, excited state being less stable, given any chance, electron will try to come back to the normal or the ground state. So when an electron is coming from excited level to the ground state, this electron has to emit energy in the form of electromagnetic radiation. So electrons coming from different excited levels will undergo different types of frequencies to be emitted. So if you make a map of the frequencies emitted, that gives you a spectrum known as emission spectrum. So these frequencies that are being emitted when an electron is coming from excited level to the ground state will appear as a bright line. So emission spectrum and the absorption spectrum, these are two types of spectrum. Atomic spectrum, which is also known as line spectrum, observed by atoms. So either we measure frequencies absorbed, then this gives you absorption spectrum, or the frequencies of the radiated emission is being measured, then this gives you emission spectrum. So every atom has got its characteristics atomic line spectra. So based on these line spectra, we can identify the atom. So we have atomic spectra. These atomic spectra is also known as line spectrum. Line spectra or line spectrum, because these spectrum, the frequencies are observed as a clear distinct line. So these are known as line spectrum, and different atoms will have different distinct line spectrum. So based on this, suppose we have the spectrum of an unknown element. We can compare the spectrum of this unknown element with those which is given in the literature, and we can easily identify the unknown atom. So we have this. This atomic spectrum is of two types, as I have discussed. One is known as absorption spectrum, the other one is known as emission spectrum. So we have these two types of spectrum, absorption spectrum and emission spectrum. Now, in absorption spectrum, frequencies of the electromagnetic radiation absorbed during excitation process is measured. So here we are measuring the frequencies or the wavelength of those electromagnetic radiation which are being absorbed by this species for excitation of electrons from lower level to higher level. Whereas in case of emission spectrum, frequencies of emitted electromagnetic radiation when an electron undergoes de-excitation process. That means when electron is coming from higher level to the lower level, that is known as de-excitation process. So here energy is absorbed, so we are measuring the absorbed frequencies. Here energy is released in the form of electromagnetic radiation, so we are measuring the frequencies or wavelength of the radiated electromagnetic radiation during the excitation process. Now, while measuring this absorption, certain frequencies are absorbed for promotion of electron from lower level to higher level. So when we make a map in a screen, those frequencies absorbed by the atom will be missing, so we'll have a dark spot in a white background. So suppose we have a white background, the screen is white background, and this white background, there are certain lines which is completely dark. So those dark lines in a white background clearly indicates that the frequencies of that corresponding line is being absorbed by the atom for promotion of electrons. So in this absorption spectrum, some dark lines will be observed, and those dark lines are missing, means those frequencies are being absorbed by the atom for promotion of electrons. So in this absorption spectrum, we have dark lines, means these are lines or the frequency is missing. Dark lines are observed. So those lines missing in the spectrum means those lines are being absorbed for promotion of electrons from lower level to higher level. That is, we are having a white background. In this white background, there are clear dark lines. So those dark lines represents the absorption spectrum. Now coming to this emission spectrum, now electron is coming from higher level to lower level. So when electron is coming from higher level to lower level, energies are emitted. Now, in this case, those lines, those radiations emitted will appear as a bright line or white spots. So if you make the screen to be dark, and in these dark there are clear bright lines observed. So those bright lines appears in a black background, gives you the emission spectrum, and those bright lines indicates that those frequencies are being released or radiated by electron when it's coming from higher level to lower level. So in case of emission spectrum, bright lines are observed. So if you look at this, the only difference is in case of emission, bright lines are observed, meaning thereby those lines are being radiated by electron when it's coming from higher level to lower level. In case of absorption, dark lines are observed in a white background, so those lines missing will be the frequencies absorbed by the electron for its promotion from lower level to higher level. So if you look at this, one is dark, the other one is bright. So it seems that both are photographic plates, photographic negatives. So this is what we call it absorption and emission spectrum. So both are similar. The only difference is one we are measuring emitter radiation, the other one we are measuring the absorbed radiation. So absorbed radiation, dark lines are appear which are being absorbed by electron. Emission spectrum, bright lines are observed, which is the frequencies radiated or given out by electron coming from excited level to the ground state. So this is atomic spectra, and as I have told you, atomic spectra, these are different spectrums are observed for different atoms. So this gives a clear idea about the frequencies that are being required for promotion of electron from one level to higher level, or the frequencies of radiation emitted when a particular electron is coming from one level to another level. So for the time being, we are focusing on this emission spectrum. So we'll observe the emission spectrum of atoms, and since we are discussing hydrogen atom being the only atom containing one electron, so this is the simplest. So we'll discuss spectrum of hydrogen atom. Spectrum of hydrogen atom, or one electron species like helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, etc. These are one electron species. So the spectrum of this hydrogen will be exactly identical to those of one electron species. So only one electron is to be promoted to any level, or only one electron is to be de-excited from any higher level to the lower level. So we have this. So during this, energies are released, and energy release is appearing in the form of electromagnetic radiation. So suppose electron is coming from N2 level to N1, where N2 is greater than N1. So electron is coming from a particular higher level to a lower level. So in this, energy is released, and this energy release is equals to x nu or hc by lambda. So whether energy is absorbed or released, this always appears in the form of electromagnetic radiation. So this is Planck's equation. So since electron is coming from N2 level to N1, so we should have energy of electron Nn to be E2 energy of electron at N1 will be E1. So this energy released will be equal to difference of this energy. Therefore, energy released is equal to delta E. So this delta E is equal to energy of electron in E into En1. So En2 minus En1. So this energy difference between the two levels will appear as the electromagnetic radiation. So therefore, look at this. This delta E is equal to Hc or Hc by it is H nu Hc by lambda. So this equals to energy of electron in a particular orbit En2. So we say this is E1 del square divided by N1 square that we have derived earlier. Minus E1 del square divided by N1 square. So we have this E1. Now E1 is a negative. So taking this into account, the negative value of E1 this 1 by lambda is equals to E1 divided by H C. So 1 by lambda is equals to E1 by H C into Z square 1 by N1 square minus 1 by N2 square, that is considering negative value of E1. E1 is always a fixed energy of electron in the first orbit of hydrogen atom. So this value E1 by Hc is defined by a constant which is known as RH Z square 1 by N1 square minus 1 by N2 square. So this equation is a very important equation which is used for measuring the wavelength or frequency of the energy emitted during the excitation process from any particular excited level to any lower level. So L1 is the final state in which the electron rests. N2 is the initial state from which electron is coming, that is higher level. So some of the authors also use this type of equation. 1 by wavelength is equals to RH Z square 1 by N, this is final square minus 1 by N initial square. So this is the final state in which electron rests. This is the initial state from which electron is coming. So this is always the higher level, this is always the lower level. So this equation both are same. So 1 by lambda, that is wave number, is equals to 1 by lambda, that is equals to RH Z square. So 1 by N1 square minus 1 by N2 square. So this equation is known as Rydberg equation. So this equation is used for measuring the wavelength or the frequency of electromagnetic radiation emitted when electron de-excites from any higher level to the ground state. So we have this equation. This is Rydberg equation, and we have a constant known as RH. This RH is known as Rydberg constant, which is equals to 1.097 into 10 to the power 7 meter inverse, or simply say it is approximately 1.1 into 10 to the power 7 meter inverse. This is Rydberg constant, because this is Rydberg constant E1 divided by H into C. This is known as Rydberg constant, whose value is always fixed, that is 1.1 into 10 to the power 7 meter inverse. This is the final state, this is the initial state. So this is the equation to be used for measuring frequency or wavelength or the wave number of the electromagnetic radiation emitted. Now, electrons may be coming from different excited levels to different load levels. Based on this, we have different types of frequencies. Some of the frequencies falls in visible spectrum, which can be observed with naked eyes. Some of the frequencies may fall in infrared radiation. Some of the frequencies may fall in ultraviolet radiation. So based on this, the frequencies of the electromagnetic radiation observed, this atomic spectrum of hydrogen or hydrogen-like system is of different types. So those types of spectrums are so based on this we have a series of lines in hydrogen or hydrogen-like system. So we have Lyman series, we have Polymer series, Lyman Balmer, we have Absorption series, we have bracket series, we have fun series. We do have other series also, but in our syllabus we have only Lyman series, Balmer series, Absorption series, bracket series, or fun series. So each series has got different frequencies, and some of the series lies in visible spectrum, some of the series lies in infrared spectrum, some of the series lies in ultraviolet radiation. So we'll take up one by one. Lyman series, Balmer series, Absorption series, bracket series. Now, for all these series, the equation to be used for measuring wave number is Rydberg equation. That is lambda is also wave number is equal to 1 by lambda r at z square 1 by n1 square minus 1 by n2 square. Now let's take up this first Lyman series. Lyman series. Now, this Lyman series, this is the only series that lies in ultraviolet radiation. This series lies in ultraviolet radiation. The frequencies emitted during this Lyman series always falls in ultraviolet. So the only series that lies in ultraviolet range is Lyman series. And this is what the scientists who discovered this series. So we have Lyman series which lies in ultraviolet range. Now Lyman series, for this Lyman series, the value of N1 is always fixed, and this is always equals to 1. So one thing you have to remember is what is the range which particular spectrum this Polymer series lies, that is ultraviolet. What is the value of N1? The final resting place when electron is coming from any excited level, that is first one, that is the ground state. So electron is always coming to the ground state from any excited level. So N1 equals to 1, but the value of N2 may be any value greater than, that is 2, 3, 4, 5, etc. Any value greater than 1, then this is known as the value of N2. So electron is coming from N2 to 1, here 3 to 1, 4 to 1, here 5 to 1. So whether this electron is coming from 5 to 1, here 4 to 1, here 10 to 1, the frequency always falls in ultraviolet radiation, and hence this is all known as Lyman series. Now, if electron is coming from 2 to 1, electron is coming from 2 to 1, then this is known as first line of transition. So if you look at this, if electron is coming from 2 to 1, that is known as first line of transition. This first line of transition is also known as alpha line, and this alpha line is the line which corresponds to minimum energy transition. Energy transition will be minimum if the electron is coming from 2 to 1 in Lyman series. If energy is minimum, then the frequency of transition will also be minimum. If frequency is minimum, then the wavelength will be maximum. So the first line of transition is also known as alpha line. First line of transition is also known as minimum energy transition. First line of transition is also known as minimum frequency transition. First line of transition is also known as maximum wavelength transition. Now for this first line of transition, the value of N2 is always equals to N1 plus 1. So first look at this, N1 is 1 plus 1, 2. So N2 is 2 to 1. If electron is coming from 3 to 1, then this is known as second line. Second line is also known as beta line. So second line, beta line, the value of N2 is N1 plus 2. Second line, N1 plus 2. If electron is coming from 4 to 1, then this is known as third line of transition, which is also known as gamma line. Value of N2 is N1 plus 3. Third line, 3. If electron is coming from 5 to 1, then this is known as fourth line of transition. This is known as delta line, and the value of N2 is N1 plus 4. If the electron is coming from infinity to 1, if electron is coming from infinitely large distance to the ground state, this is known as last line of transition. So last line of transition is also known as maximum energy transition. If energy is maximum, then frequency will also be maximum. If frequency is maximum, wavelength will be minimum. So minimum wavelength transition is last line of transition, for which N2 is infinity and 1 is 1. Maximum minimum wavelength, it means maximum frequency. If frequency is maximum, energy is maximum. So this is various terms that often we use for all these series. So this is for all these except the value of this and 1. So for every series, Lyman, Balmer, partial bracket fund, the first line is always known as alpha line, minimum energy, minimum frequency, maximum wavelength, N2 is N1 plus 1. Second line, beta line, N2, N1 plus 2. Third line, gamma line, N2, N1 plus 3. Fourth line, delta line, N2 is equals to N1 plus 4. Last line, maximum energy, maximum frequency, minimum energy, for which N2 is equals to infinity. So these characteristics, first, second, third, fourth, last, alpha, beta, gamma, delta, that is common for all these series. So for this Lyman series, since we are discussing Lyman series, this is a transition 2 to 1, 3 to 1, 4 to 1, 5 to 1, and infinity to 1. Now, if this is the case, for this Lyman series, the value of N1 is always fixed, that is 1. N2 can have any value greater than 1. So, therefore, wave number for this Lyman series, or 1 by wavelength for this Lyman series, is equals to RH. For hydrogen, Z is equals to 1, or simply we can write down Z square also. So 1 by 1 square minus 1 by n square. So therefore this is RH Z square 1 minus 1 by n square. So this is the equation applicable for Lyman series. So for this Lyman series, what we have to remember is the value of N1, value of N2 for this first line, second line, third line, and the meaning of alpha, beta, gamma, delta, and energy minimum and maximum energy transition. So if this is the case for this, then let me give you equation for this minimum energy transition and the maximum energy transition. So alpha line or minimum energy or minimum frequency or maximum lambda. So 1 by wavelength, that is maximum, because wavelength should be maximum for this alpha line, is equals to RH Z square. N2 is 2 to 1, so 1 minus 1 by 2 square, that is 4. So this comes out to be 3 by 4 RH Z square. For hydrogen, Z is 1, so we can find out what is the maximum value of wavelength of transition for this Lyman series. Similarly, look at this last line. For this last line is also known as maximum energy or maximum frequency or minimum wavelength transition. That is last line when N2 is equals to infinity. So for this 1 by lambda minimum is equals to RH Z square. 1 minus 1 by infinity square is infinity, so 1 by infinity is 0. So this is equals to RH Z square. So for this Lyman series, this is the equation applicable. We can change the value of n. This is first line, this is last line. Minimum energy transition, maximum energy transition, maximum wavelength transition, minimum wavelength transition, minimum frequency transition, maximum frequency transition, and this is the characteristics of alpha, beta, gamma, delta. So look at this. So main point is Lyman series first lies in ultraviolet radiation. Value of N1 for Lyman series is 1. N2 may be any value greater than 1. Depending on the transition, we can classify into alpha, beta, gamma, delta. And this is the equation applicable. So this is how we can use this equation to find the frequency or the wavelength or the wave number of the electron transition. So this is Lyman series. Now coming to next, that is Polymer series. Second series, that is Polymer series. Now these Polymer series lies in visible region. So the only series that lies in visible is Polymer series. Lyman series lies in ultraviolet region. Polymer series lies in visible spectrum. Now for this Polymer series, the value of N1 is always fixed and this is always equals to 2, and N2 may be any value greater than 2. So when an electron is coming from any excited level to second level, that is first excited state, then the frequencies emitted or the wavelength emitted always falls in a visible spectrum, and that spectrum is known as Polymer series. So that particular area of spectrum is known as Polymer series, which always lies in the visible spectrum. So for Polymer series visible spectrum, the value of N2, so N1 is 2, N2 is always greater than 2. So if electron is coming from 3 to 2, that is known as first line. Electron is coming from 4 to 2, that is known as second line. Everything remains same. Electron is coming from 5 to 2, third line, gamma line. Electron is coming from 6th level to first excited state, 4th delta. Electron is coming from infinity to the first excited state, that is last line or maximum energy transition. So this is the characteristics. Now since the value of N1 is 2, the equation applicable for this Polymer series, so we say this is Polymer series R8 Z square 1 by N1 is 2, so we say 1 by 2 square, that is 4, minus 1 by N square. This is the Rydberg equation as applicable to the Polymer series. Now first line, minimum energy transition, for which the value of N2 is N1 plus 1. So alpha line is 1 by 4 minus N2 is 2, so 1 by 3 square means 1 by 9. So when solving this, five by 36 R8 J square. So this is maximum wavelength transition, that is the first line, or minimum energy transition. Last line, that is maximum energy or minimum wavelength, that is R8 J square 1 by 4 minus 0, because 1 by infinity is 0, so this is equal to R8 J square by 4. So this is how we use Rydberg equation to find the values of wavelength or wave number for Polymer series. So the first series, Lyman was a ultraviolet. Second series, Polymer a visible. Then we have Paschen series. These Paschen series lies in near infrared region. So we have third series, that is Paschen series. Paschen series. So partition series lies in infrared region. For Polymer series, electron was coming from any excited level to the first excited state, that is N1 is to 2. For partition series, if electron is coming from any excited level to the second excited state, that is known as 3, and N2 is any value greater than 3. So again, based on this, electron is always coming to the third level, that is second excited state. Now electron is coming from 4 to 3, first line of transition alpha line. Now electron is coming from fifth level to third level, second line beta line. Electron is coming from sixth level to third level, that is third line. Electron is coming from seventh level to third level, delta line. Electron is coming from infinity to third, that is last line. So we have this partition series, and as applicable for this is, let's say this is PS partition series. 1 by n1, n1 is 3, so 3 square is 9 minus 1 by n square. That is Rydberg equation for partition series. Alpha line minimum energy 1 by 9, so that is first line, so n2 is 4, so 4 square is 16. So we have this equation. Last line, electron is coming from infinity to the second excited state, so 1 by 9 minus 0, so this comes out to be RHZ square divided by 9. So this is how we define minimum frequency, maximum frequency transition for this partition series. The third next series, so bracket series. Again, this bracket series lies in mid-infrared, middle portion of infrared. So again, this lies in infrared region, but which infrared region? Middle of the infrared region. N1 is always fixed, that is 4, and N2 is any value greater than 4. So we can have 5, 6, 7, 8, etc. So electrons are always coming to the fourth level, that is third excited state. Now electron coming from fifth level to 4, alpha line, 6 to 4, beta line, 7 to 4, delta gamma line, 8 to 4, delta line, that is last line. And the equation applicable for this bracket series, so 1 by n1 is 4, 4 square is 16 minus 1 by n square. Alpha line, minimum line, so 1 by 16 minus 5 square is 25. Last line, so this is 1 by 16, so this comes out to be 60. So this is bracket series. And last we have fun series. Now these fun series, this lies in far infrared. So these are the three series that lies in infrared. So Lyman ultraviolet, Balmer visible, partition near infrared, bracket middle of infrared, fun far infrared. So these three, partition, bracket, fun, lies in infrared region. So for this fun series, again this lies in infrared region, the value of n1 is always 5 and the value of n2 is any value greater than 5. Then the first line of transition alpha, beta, gamma, delta, and the last line. The electron is coming from 6 level to 5 first line, 7 to 5 second, 8 to 5 third, 9 to 5 fourth, infinity to 5 last line. So equation applicable is one series. So maximum wavelength, that is alpha line. So this equals to 1 by 25 minus 1 by 36. Last line, so this is last line. So for all this information is, the main point to be remember is what is the spectrum in which this series lies and what is the value of n1 for this series. So once we know the value of n1, we can easily define the energy for transition, wavelength for this transition, or frequency for this transition. So this is 5 different series that is observing spectrum of hydrogen, and each series appears as a clear distinct line. So the frequency of all these series will show a clear distinct line, that is bright lines in the screen. So from the bright line we measure the frequencies of the radiation emitted during this de-excitation process. So this is the spectrum. Now when we observe this spectrum, now an electron may be coming from any excited level to the ground state. So during this de-excitation process, what is the maximum number of lines that could be observed? So one point you have to keep in mind, maximum number of lines or the maximum number of wavelength or the maximum number of frequencies. Maximum number of lines observed when an electron jumps from N2 to N1 level. So electron is coming from any excited level N2 to lower level N2. So how many maximum lines can be observed? How many maximum frequencies or how many distinct wavelength lines can be observed? So this maximum number of lines is equals to summation of this N2 minus N1. Simply we say summation of delta N. So this will help you in identifying maximum number of lines possible for objective as well as subjective type questions. So I'll give you an example with this. Suppose if electron is coming from 4, N2 is 4 to N1 1. So electron is coming from 4th level to ground level. So maximum lines that can be observed, that is summation of delta n. So summation of delta n is n2 minus n1. So we have 4 minus 1, that is 3. So this is p plus 2 plus 1. So how many lines are possible? 6 lines are possible. So when an electron jumps from 4th level to ground state, there are 6 possible lines that could be observed. Though electron is coming to ground state, so the maximum lines are possible, electron is coming by step process. So look at this, what are the possible lines here? So electron coming from 4th to ground. So the possibilities is, now direct electron is coming from 4 to 1. So one possible. So if electron is coming direct from 4 to 1, then this gives you one line. One line will be observed here. Now electron coming from 4 to 1, final resting place is 1, so this is under Lyman series ultraviolet. Now the second possibility is electron is coming from 4 to 3, then 3 to 1, this is also possible. Now force electron comes from 4 to 3, then direct 3 to 1. Now electron coming from 4 to 3 will have one line, so one line is possible here. Electron coming from 3 to 1, again one line is possible. Electron coming from 3 to 1, final resting place is 1, so this comes in Lyman series or ultraviolet. Electron from 4 to 3, N1 is 1, N2 is 2, N2 is 3. So N1 is 1, N1 is 2, N1 is 3. So that was in Absorption series. So this is Absorption series and this is infrared. So we have two lines, one line corresponding to Absorption series, that is infrared, second line corresponding to Lyman series ultraviolet. So we have two lines here. Now the third possibility is electron coming from 4 to 3, then again 3 to 2, then finally 2 to 1. 4 to 3 already we have counted here. Then we have 3 to 2, we will have one line, 2 to 1 will have one line. Now look at this, 2 to 1, finally electron is resting at ground state, so this comes in Lyman series ultraviolet. Electron coming from 3 to 2, that is Polymer series, and this lies in visible spectrum. So again, how many lines are observed here? 2. Now look at this, we have 4 to 1, one line. 4 to 3, one line. 3 to 1 line. Now 4 to 3, 3 to 2, 2 to 1. There is one possibility is also electron may jump to 4 to 2 also, then 2 to 1, this is also possible. 2 to 1 already we have counted here, that is ultraviolet Lyman series. Then we have 4 to 2, final resting place is 2, so this comes under Polymer series and this is visible, so we'll have one line. So total number of lines is 2 plus 2, 4 plus 2, 6. There are 6 possible lines. So during any transition from any excited level to ground state, we can calculate how many maximum lines are observed possible by use of this formula, summation of delta n. And once we know the this, we can also find how many lines appears in ultraviolet, how many lines appears. So let me give you one more example here. Now, if electron is coming from 6 to 2, that is N2, this is N1. Maximum lines possible. So this is equals to summation of delta n. So this equals to 6 minus 2 summation, that is summation of 4. So 4 plus 3 plus 2 plus 1. So this is 7, 10. There are 10 possible lines possible. So this is from just from how to find the number of lines possible when electron is undergoing the excitation process. So the formula is summation of delta n that is to be used. Now this is the 5 different series observed for hydrogen or hydrogen-like species. Now diagrammatically this can be shown in this way. Suppose let us be 10 is equals to 1, 2, 3, 4, 5, 6, 7. This n equals to 1, this is known as ground state. This is first excited state, second excited state, etc. This is third, fourth, fifth, sixth excited state. This is ground state, the lowest. Now, electron may be coming from this excited state, any of this excited state, to this ground state. If electron is coming from any of this excited state, so we have a number of states. I'm just saying this is the first, second, third, fourth, fifth, etc. If electron is coming from any of this excited state to the ground state, then this is known as Lyman series. Now, electron may also come from any of this excited state to this first excited state. If electron is coming from any of this excited state to first excited state, then this series is known as Polymer series that lies in visible spectrum. Now, if electron is coming from any of this excited state to this second excited state, then this series is known as Absorption series. Now, if electron is coming to third excited state, then this is known as bracket series. If electron comes to the fourth excited state, then this series is known as fun series. So we have these 5 series. Now this Lyman series that lies in ultraviolet, Polymer series that lies in visible, Absorption series that lies in near infrared, bracket, mid infrared, fun, far infrared. So these 3 lies in infrared region, and the frequencies, so what is 1 by wavelength is equals to RH Z square 1 minus 1 by n square. For this 1 by wavelength is equals to RH Z square 1 by 4 minus 1 by n square. For this 1 by wavelength is equals to RH Z square 1 by 9 minus 1 by n square. For this 1 by wavelength is equals to RH Z square 1 by 16 minus 1 by n square. And for this 1 by wavelength is equals to RH Z square 1 by 25 minus 1 by n square. So this is the 5 series observing hydrogen or hydrogen like series. So this is how we use series. So let me show you some examples. For helium plus, electron is coming from fourth level to first excited state. Calculate the wave number. So we have helium plus electron is coming from fourth level to the first excited state. So fourth level means n equals to 4. First excited state means n equals to 2. This is ground state, this is the first excited state. First excited state, so this is the value of n1, this is the value of n2. Electron is coming from 4 to 2. So if electron is coming from 4 to 2, so this lies in Polymer series. Therefore, the equation for this wave number is equals to 1 by wave n is equals to RH z square 1 by n1 square minus 1 by n2 square. So RH z helium z equals to 2. So this is 4. 1 by n1 is 2, so 1 by 4 minus 1 by n2 square 1 by 4 square. So therefore wave number is equals to RH 1 minus 1 by 4, multiply this by 4. So that is 3 by 4 times RH. So if this is the case, we can find out therefore wavelength will be equals to, that is inversely related to 4 by 3 RH. This is the wavelength for this transition. If this is the wavelength, then we can also find this frequency. So wavelength frequencies are related via speed of light c. So this is hydrogen light spectrum that we discuss is emission spectrum, in which the frequency of light emitted is observed as a clear distinct light. So this is hydrogen light, in which we use the concept of quantized energy concept that was defined by Planck's equation. So Bohr's theory is basically based on the quantized energy concept of electron. Based on this quantized energy concept, we say electron energy, when this absorption energy or this release energy, this is always in the form of small packets, that is discontinuous process. Now this is an improvement over this Rutherford model. But along with this, there are some demerits also. Now let me give you the demerits of this Bohr's theory or disadvantage of this Bohr's theory. Disadvantage or demerits of Bohr's theory. Disadvantage of Bohr's theory. First disadvantage of Bohr's theory is, whenever we talk of this Bohr's theory, we always talk of hydrogen or hydrogen light. That means an species containing only one electron. So that means this Bohr's theory is applicable for only one electron, that is hydrogen or hydrogen light. But if the system contains more than one electron, then this Bohr's theory will not be applicable. So the most important demerit of this theory is applicable only to one electron species, that is hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, etc. So these are species containing one electron. If the system contains more than one electron, then the theory fails here. Second demerit for this theory is, though we consider quantized energy concept, based on this we observe clear distinct lines in spectrum. We'll continue with next class.